Hello everyone. Today we'll study the natural logarithmic function. The natural logarithmic function is defined as ln of x equal to the integral from 1 to x 1 over t dt, where x is greater than 0. It represents area under the curve y equal to 1 over t. It represents area under the curve y equal to 1 over t. The graph of y equal to 1 over t looks like this. That's the graph y equal to 1 over t. It represents area under the curve from 1 to x. Suppose 1 is here, x is here. The natural logarithmic function represents area under the curve from 1 to x. So it represents area here under the curve from 1 to x. We can see that here. As x varies, the value of the function changes. So ln of x is a function. It represents area under the curve y equal to 1 over t from 1 to x. As x change, the area change. So that's a function of x. And based on the graph, we can see that if s is greater than 1, then ln of x represents area under the curve from 1 to x. If we integrate from left to right, and the area is above x-axis, this area is positive, which means ln of x is positive. So if s is greater than 1, then ln of x is greater than 0. If x is less than 1, then x is somewhere here. ln of x represents area under the curve from 1 to x. From 1 to x, if s is less than 1, we integrate from right to left. If we integrate from right to left, the area is negative. So if s is less than 1, ln of x is less than 0. Or if s equal to 1, what's ln of 1? ln of 1 represents area under the curve from 1 to 1. Integral from 1 to 1, there's no area. If we take integral from 1 to 1, there's no area under the curve. This area is 0. So ln of 1 is 0. If s equal to 1, ln of 1 is 0. Next, let me show you some laws of logarithms. Let x and y be any positive numbers, and let r be any rational number. Then we have the following laws. First law says ln of x times y equal to ln of x plus ln of y. Second law says ln of x over y equal to ln of x minus ln of y. And the third law says ln of x to the power r equal to r times ln of x. Let's prove these laws. How can we prove the first law? What's ln of sy? We know that ln of x is the integral from 1 to x 1 over t dt. So for ln of sy, we plug in xy to the upper limit. For ln of sy, we plug in xy to the upper limit. So ln of sy is integral from 1 to sy 1 over t dt. This integral can be rewritten as integral from 1 to x 1 over t dt plus integral from x to sy 1 over t dt. The first part, we can clearly see that this is ln of x. How about the second part? How do we show the second part is ln of y? So for the second part, let's apply U substitution for the second part. For the second part, let's apply U substitution. Let U equal to t over x. For the second part, let U equal to t over x. Then, what's the U here? We take derivative here with respect to t. The variable here is t. Take derivative with respect to t. I get 1 over x dt. Then I can multiply both sides by x. Here I treat x as a constant. I can multiply both sides by x. If I multiply both sides by x, I get x du equal to dt. Now, if I plug in, what's t here? For t, I can solve the equation for t from here. U equal to t over x. If I multiply both sides by x, t equal to ux. If I multiply both sides by x, t equal to ux. So I get 1 over ux times dt. dt is x du. Now how about upper and lower limit? For upper and lower limit, we plug in x for t and plug in sy for t. Here variable is t. We plug in both x and sy for t. For the lower limit, if I plug in s for t, I get s over x. That's 1. For the upper limit, if I plug in sy for t, I get sy over x, which is y. Then I can cancel x. If I cancel x, I can integral from 1 to y, 1 over u du. That's exactly the same as 1 over t dt. So this is ln of y. That's how we prove ln of sy equal to ln of x plus ln of y. That's the proof for the first law. ln of sy equal to ln of x plus ln of y. Next, how can we prove the second law? Second law, ln of s over y. That can be written as integral from 1 to x over y, 1 over t dt. That's the upper limit. Lower limit is 1. Upper limit is x over y, 1 over t dt. We try to show this equal to ln of x minus ln of y. So this integral can be written as integral from 1 to x, 1 over t dt, plus integral from x to s over y, 1 over t dt. The first part, you can see that this is ln of x. Integral from 1 to x, 1 over t dt. This is ln of x. How about the second part? How can we show the second part is negative ln of y? So for the second part, again, use the u substitution. Let u equal to y over x times t. Then, for du here, I treat s and y as constant. T is a variable. I treat s and y as constant. I get y over x times dt. We have a dt here. We don't have y over x. So I multiply both sides by the reciprocal, s over y. If I multiply both sides by s over y, I get s over y du equal to dt. So I get dt here. And what's t? Same thing for t here. I multiply both sides by the reciprocal, s over y. So u equal to y over xt. If I multiply both sides by the reciprocal, s over y u equal to t. So that's dt, that's t. Plug in. This integral can be rewritten as 1 over s over y times u times dt is s over y times du. How about limit here? For limit, we plug in upper and lower limit for t. Here t is the variable. We plug in the upper and lower limit for t. On the bottom, if I plug in x for t, if I plug in s for t, y over x times x is y. That's the lower limit. For the upper limit, if I plug in s over y for t, I get y over x times s over y, which is 1. If I plug in s over y for t, I get y over x times s over y, which is 1. Then here, in the integral, s over y can cancel. I get 1 over u du. For this integral here, if I interchange in upper and lower limit, I change the sign. I make it negative. Integral from 1 to y, 1 over u du. And we can see that this is ln of y. So we have ln of x minus ln of y. That's the proof for the second law. The third law is ln of x to the power r equal to r times ln of x. How can we prove the third law? Here, for the third law, let's consider two cases. Case 1, r equal to 0. If r equal to 0, the left-hand side equal to ln of x to the power of 0. X to the power of 0 is 1. What's ln of 1? We know that ln of 1 is 0. Every end on the curve from 1 to 1 is always 0. Now from the right hand side, we have r times ln of x. Since r is 0, I get 0 times ln of x, which is also 0. So in the first case, left hand side equal to the right hand side. So ln of x to the power r equal to r times ln of x if r is 0. Case 2. What if r is not 0? What if r is not 0? How can we prove this? If r is not 0, then ln of x to the power r, that's the integral from 1 to x to the power r, 1 over t dt. That's the upper limit. Integral from 1 to x to the power r, 1 over t dt. Now, how can we prove this? Here, let's make a u substitution. Let u equal to t to the power of 1 over r. Since r is not 0, I can write t to the power of 1 over r. Since r is not 0. Next, to make it a little easier, I raise both sides to the power r. Make it a little easier, I raise both sides to the power r. I get u to the power r equal to t. Then, take derivative on both sides. On the left side, if I take derivative, I get r times u to the power of r minus 1 du equal to dt. Take derivative on the left side and right side. Then, substitute. T is u to the power r. Dt is r times u to the power of r minus 1 du. What's the limit here? For the limit, we plug in upper lower limit for t. The variable is t here. Plug in both upper lower limit for t. If I plug in 1 for t, 1 raised to any power is 1. If I plug in s to the power r for t, I get s to the power r raised to the power of 1 over r. X to the power r raised to the power of 1 over r. If I plug in s to the power r for t, I get s to the power r raised to the power of 1 over r. These two are cancel. These are cancel. We get x to the power 1, which is x. That's an upper limit. Then simplify. If I cancel u to the power of r minus 1 and u to the power of r, we see that the power on the bottom is 1 more larger than this. So if I cancel, there's 1u left, because r is 1 larger than r minus 1. If I cancel the power, I have 1u left on the bottom. That's r stays here, du. And then, since we treat r as a constant, we can pull out constant r. We get r times integral from 1 to x, 1 over u du. And we know that 1 over u du is the same as 1 over t dt. This is ln of x. That complete the proof that ln of x to the power r equal to r times ln of x. That's a proof of the third law. That's a proof of the third law. Next, let's look at some examples. Expand each of the following expressions. First expression, ln of x cubed times y to the power 4. So, by the first law, we can always convert multiplication to addition. This expression can be rewritten as ln of x cubed plus ln of y to the power of 4. Then, next, by the third law, we can always bring exponent to the front. By the third law, we can always bring exponent to the front. So this expression can be written as 3 ln of x plus 4 ln of y. That's how we expand this expression. Next example, ln of a to the power 4 over b squared times square root of c. So, for this expression, by the second law, we can always change division to subtraction. By the second law, we can always change division to subtraction. So it can be rewritten as ln of a to the power 4 minus ln of b squared square root of c. Next, for the second part here, I can change multiplication to addition by the first law. For the second part here, I can change multiplication to addition by the first law. So I got ln of a to the power 4 minus ln of b squared plus ln of square root of c. I can change multiplication to addition. Next, distribute negative sign. I get ln of a to the power 4 minus ln of b squared minus ln of square root of c. Square root of c can be rewritten as c raised to a half. Next, by the third law, I can always bring exponent to the front. By the third law, I can always bring exponent to the front. I get 4 ln of a minus 2 ln of b minus half times ln of c. That's how we expand this expression. Next example, combine each of the following expressions as a single logarithm. First example, 2 times ln of x minus 5 times ln of y. How can we combine this as a single logarithm? So, first of all, by the third law, we know that we can always bring exponent to the front. The opposite says we can always bring the coefficient back as exponent. The opposite says if there's a coefficient in the front, I can always bring it back as exponent. So, if there's a coefficient 2 in the front, I can bring it back as exponent. This can be rewritten as ln of x squared. So if there's a 5 here, I can bring 5 back as exponent. But as ln of y to the power of 5. Then, by the second law, since I can convert division to subtraction, similarly I can convert subtraction back to division. By the second law, this can be written as ln of x squared over y to the power of 5. That's how we combine this expression as a single logarithm. Next example, half of ln of a minus 1/3 of ln of b plus 2 ln of c minus 3 ln of d. First step, if there's a coefficient in the front, bring coefficient back as exponent. If there's a coefficient in the front, bring coefficient back as exponent. By the third law, this can be written as ln of a raised to a half minus ln of b raised to a third plus ln of c raised to power 2 minus ln of d raised to power 3. If there's a coefficient in the front, we can first of all bring coefficient back as exponent. Next, let me first of all combine the positive term together and the negative term together. Let me first of all group the positive term together and the negative term together. If I group the positive term together, I get ln of a to a half plus ln of c squared. If I group negative term together, I get ln of b to a third plus ln of d to the power 3. Then, by the first law, since I can convert multiplication to addition, the opposite says I can convert addition back to multiplication. So it can be written as ln of a to a half times c squared by the first law. Minus ln of b to a third times d to the power of 3. Next, by the second law, we can always convert division to subtraction. The opposite says I can always convert subtraction back to division. So it can be written as ln of a to a half c squared divided by b to a third d to the power 3. Then the final answer can be written as square root of a times c squared over cube root of b times d to a third. That's how we combine this expression as a single logarithm. Next example, 2 ln of x plus 1 minus ln of x squared minus 1. How can we combine these expressions? First of all, if there's a coefficient in front, I can bring coefficient back as exponent. So first term can be written as ln of x plus 1 squared minus ln of x squared minus 1. Next, by the second law, I can convert subtraction back to division. So it can be written as x plus 1 squared over x squared minus 1. Then, if we simplify, the denominator can be factored as x plus 1 times x minus 1. If I cancel x plus 1 from top and the bottom, the final answer is ln of x plus 1 over x minus 1. That's the final answer in the simplest form. Next, I'll show you the graph of the function y equal to ln of x. Before I show you the graph, let's look at the limit first. How can we take this limit? Limit as x approaches to infinity, ln of x. How can we take this limit? Taking this limit directly is not easy. So let me first of all let function f equal to ln of x. Consider this. What's f of 2 to the power of n? What's f of 2 to the power of n? F of 2 to the power of n can be written as ln of 2 to the power of n. And then, by the third law of logarithm, I can bring exponent to the front. Write it as n times ln of 2. ln of 2, since 2 is more than 1, we know that this is a positive number. Since 2 is more than 1, ln of 2 is a positive number. We know that if x is more than 1, ln of x is always positive. Here, since 2 is more than 1, ln of 2 is always positive. So here we can see that as n approaches to infinity, f of 2 to the power of n also approaches to infinity. Infinity times a positive number is infinity. So as n approaches to infinity, f of 2 to the power of n approaches to infinity. Which means, if f of something approaches to infinity, that means the function f of x is not bounded above. So the function f of x is not bounded above. if I plug in something, I can make it infinity. That means f of x, function f of x, is not bounded above. Next, if we take derivative for function f, what do we get? If we take derivative for function f, what do we get? That's derivative of ln of x. And ln of x is integral from 1 to x, 1 over t dt. By fundamental theorem of calculus, when we take a limit for the integral from 1 to x, I plug in x for t. That's 1 over x. Since x is always greater than 0, for the function ln of x is always greater than 0. Since s is greater than 0, f prime of x equal to 1 over x. 1 over a positive number is always greater than 0. If the derivative is always greater than 0, then the function is always increasing. So f is always increasing. Also, since f is differentiable, then it must be continuous. Then f is continuous. So together, since f is continuously increasing, and it's not bounded above, then as s approaches infinity, f of x must be infinity. Since f is continuously increasing and it's not bounded above, there's no upper bound, it's not bounded above, then as s approaches infinity, function f must approach infinity. Hence, as s approaches infinity, ln of x must be infinity. So that's the first limit. As s approaches infinity, ln of x must be infinity. Next, let's look at a different limit. How can we take this limit? Limit as s approaches 0 from right side, ln of x. How can we take this limit? So, for this limit, think of this. Let t equal to 1 over x. Let's let x equal to 1 over t. Then, similarly, t is the same as 1 over x. Here we can see that as s approaches to 0, as s approaches to 0 from right side, t is 1 over 0. 1 divided by a very, very small number become very, very large. So t approaches to infinity. As s approaches to 0 from right side, t approaches to infinity. 1 over a very, very small number become very, very, very large. So as s approaches to 0, t is 1 over 0, which is a very, very large number. That's infinity. So this limit can be written as limit s approaches to 0 from right side, ln of x. limit s approaches to 0 from the right side is the same as saying t approaches to infinity. L1 of x can be written as 1 over t. So this limit can be written as limit t approaches to infinity Ln of t raised to -1. 1 over t can be written as t raised to -1. Then, by the third law of logarithm, I can bring exponent to the front. That's the limit t approaches to infinity -1 times Ln of t. And then -1 is a constant. I can bring it outside the limit. That's -1 times the limit t approaches to infinity Ln of t. And we know that as t approaches to infinity, Ln of t is infinity. As s approaches to infinity, Ln of x is infinity. Same thing works for t. As t approaches to infinity, Ln of t is infinity. So we get -1 times infinity, which is negative infinity. So this limit, as s approaches to 0 from the right side, Ln of x is negative infinity. Next, let me show you the graph of a function f of x equal to Ln of x. Since we know that the limit as s approaches to infinity, Ln of x is infinity, that means there are no horizontal asymptote. For another limit as s approaches to 0 from the right side, Ln of x is negative infinity. That means there is a vertical asymptote at 0. There's a vertical asymptote at s equal to 0. So there are no horizontal asymptote, and there's a vertical asymptote at s equal to 0. Also, we know that Ln of 1 is 0. That means there's an s-intercept at 1. Ln of 1 is 0, means there's an s-intercept at 1. And also we know that the derivative f prime of x is 1 over x, which is positive for all x greater than 0. That means the function f is increasing. If the derivative is positive, it means function f is increasing. What's the second derivative? For the second derivative, take derivative again. We know that 1 over x can be written as x raised to -1. If we take derivative again, we get -1 times x raised to -2. That can be rewritten as -1 over s squared. This is always negative for x is greater than 0. This is always negative. It doesn't matter s is positive or negative. This is always negative. X squared is always non-negative. 1 over a non-negative number, 1 over a positive number is positive. If I add negative sign in the front, it's negative. So f double prime of x is always less than 0. That means function f is always concave down. Function f is always concave down. 1 over s squared, that's a perfect square, that's always positive. Positive number over a positive number is positive. And plus the negative sign in the front. Negative positive is negative. So f is always concave down. If f double prime is less than 0, it's negative. If f double prime is negative, f is always concave down. So, based on this information, let's sketch a graph. there's no horizontal asymptote, there's a vertical asymptote at 0. There's a vertical asymptote at 0. And it approaches to negative infinity. As s approaches to 0 from the right side, function f approaches to negative infinity. S-intercept is 1. Function is always increasing. Increasing concave down. It's always concave down. Then connect this curve. Using a smooth curve, connect this point, make it increasing concave down. It looks like this. That's a graph y equal to Ln of x. It's always increasing, it's concave down. S-intercept is 1. There's a vertical asymptote at 0. And there's no horizontal asymptote. That's a graph of a function y equal to Ln of x. Next, let me introduce Euler's number E. First of all, let f of x equal to Ln of x. Since f is continuous, f of 1 is 0. F is continuous, f of 1 is 0. And as s approaches infinity, f of x also approaches to infinity. Since f is continuous, f of 1 is 0. And as s approaches to infinity, f of x also approaches to infinity. Then, by intermediate value theorem, there exists a real number c such that f of c equal to 1. Since f of 1 is 0, as s approaches to infinity, f of s approaches to infinity. Then, by intermediate value theorem, there exists a real number c such that f of c equal to 1. By intermediate value theorem, there exists a real number c such that f of c equal to 1. And this real number c is called Euler's number, denoted by E. And this real number c is called the Euler number. It's called Euler's number, denoted by E. Here, since f of x is Ln of x and f of c equal to 1, that means f of c equal to Ln of c equal to 1. And also, this real number c is denoted by E. That means Ln of E equal to 1. This E is called an Euler number, which make Ln of E equal to 1. And using calculator, E is a constant. It's approximately 2.718 and so on. E is a constant. It's approximately 2.718 and so on. That's an Euler number E. So for logarithmic functions, keep the following laws and properties in mind. When we have Ln of x times y, we can always convert multiplication to addition, write it as Ln of x plus Ln of y. For Ln of x over y, we can always convert division to subtraction, write it as Ln of x minus Ln of y. And for ln of x raised to power r, we can always bring exponent to the front, write as r times ln of x. The same thing works on the other direction. We can always convert addition back to multiplication, and convert subtraction back to division. We can always bring coefficient back as exponent. And for the property of logarithmic functions, keep in mind that ln of 1 is always 0. ln of e is always 1. As x approaches infinity, ln of x approaches infinity. As x approaches 0 from the right side, ln of x approaches to negative infinity. So keep these laws and properties in mind. Next, let me show you the derivative of natural logarithmic function. How can we take derivative for natural logarithmic function? We know that the natural logarithmic function is the integral from 1 to x, 1 over t dt. When we take derivative, applying the fundamental theorem of calculus, we plug in upper limit x for t, and that's 1 over x. So keep in mind that the derivative of ln of x is always 1 over x. And if the function is ln of f of x, then by chain rule, the derivative is 1 over the inside function times the derivative of the inside function. If the function is in the form of ln of f of x, then by chain rule, the derivative is 1 over the inside function times the derivative of the inside function. So that's how we take derivative for natural logarithmic function. Next, let's look at some examples. Differentiate each of the following functions. How can we take derivative for the function f of x equal to ln of x squared plus 3x plus 4? So this function is in the form of ln of some function inside. So its derivative is 1 over the inside function, 1 over the inside function, times the derivative of the inside function by chain rule, times the derivative of the inside function. That's 2x plus 3. So for the final answer, write it as 2x plus 3 over x squared plus 3x plus 4. That's how we take derivative for this function. Next example, f of x equal to x times ln of x. How can we take derivative for this function? When we have two functions multiplied together, use product rule. When we have two functions multiplied together, use product rule. Product rule is derivative of the first times the second plus the first times derivative of the second with product rule. So apply product rule here. Derivative of the first times the second plus the first times derivative of the second. Derivative of ln of x is 1 over x. If we simplify, 1 times ln of x is ln of x. X times 1 over x is 1. That's the derivative of this function. Next example, f of x equal to ln of sine x plus cosine x squared. This function is in the form of ln of a function. So if we take derivative directly using chain rule, we have f prime of x equal 1 over this function sine x plus cosine x squared times the derivative by the chain rule times derivative of this function. Here use chain rule again. 2 times sine x plus cosine x raised to power 1. Then by chain rule times the derivative of the inside function. Derivative of sine is cosine. Derivative of cosine is negative sine. If we simplify, we can see that here sine x plus cosine x looks exactly the same. Cancel one of them out. We get 1 over sine x plus cosine x times 2. This can cancel. Times cosine x minus sine x. Then for the final answer, we can bring 2 to the front. Bring cosine x minus sine x to the numerator. I get cosine x minus sine x over sine x plus cosine x. That's the derivative of this function. However, there's a simpler way. For this problem, there's a simpler way to take derivative. For this function, f of x equal to ln of sine x plus cosine x squared. If we use the law of logarithm, simplify the function first, what do we get? The third law of logarithm says if there's exponent, we can bring exponent to the front of logarithm. So if I bring 2 to the front, I get 2 times logarithm of sine x plus cosine x. If we simplify first, then take derivative, what do we get? Now when we take derivative, this number 2 is a constant multiple. It stays the same. We have ln of a function here. So take derivative using chain rule. We get 1 over the inside function sine x plus cosine x times the derivative of the inside function. Derivative of sine x is cosine x. Derivative of cosine x is negative sine x. And then for the final answer, we can bring cosine x minus sine x to the numerator. We get 2 times cosine x minus sine x over sine x plus cosine x. We get exactly the same answer, but taking derivative in this way is much easier. Taking derivative in this way is much easier. If we bring exponent to the front first and then take derivative, it will be much easier. Next example. F of x equal to ln of s squared sine cube x. If we take derivative directly using chain rule, f prime of x is 1 over the inside times the derivative of the inside. For the derivative of the inside, we have s squared sine cube of x. We need to use product rule and chain rule, which may be too much work. What if we simplify first? Then take derivative? It may be much easier. Let's try. This way works, but maybe too much work. If we take 1 over the inside, and then times derivative of inside, here we need to use product rule and chain rule. It works, but maybe too much work. What if we simplify first using the law of logarithm? What if we simplify first? If we simplify first using the law of logarithm, we can first of all convert multiplication to addition using the first law of logarithm. So we get ln of x squared plus ln of sine cube of x. Next, by the third law of logarithm, we can bring exponent to the front. We get 2 ln of x plus 3 ln of sine x. Simplify first, then take derivative. ln of x, we want to take derivative, that's 1 over x. For ln of sine x, if I take derivative, I get 1 over sine x. Then by chain rule, times derivative of sine x, which is cosine x. If we simplify, we get 2 over x plus 3 times cosine x over sine x. And we know that cosine x over sine x is cotangent x. Taking derivative in this way is much easier than taking derivative directly. So if we simplify the function using the law of logarithm, simplify the function first, and then take derivative, it will be much easier than taking derivative directly. Next example. F of x equal to ln of square root of s squared plus 2x over s cubed minus x. So let's simplify the function first and then take derivative. Otherwise, it may be too complicated. So for ln of square root can be written as power of 1 over 2. We have s squared plus 2x s cubed minus x. Then by the law of exponents, by the law of logarithm, we can bring exponent to the front. We get half of ln of s squared plus 2x over s cubed minus x. Here we have division here. By the second law of s logarithm, we can convert division to subtraction. It can be written as f of x equal to half of ln of s squared plus 2x minus ln of s cubed minus x. That's the second law of logarithm. We can convert division to subtraction and then take derivative. It will be much easier. When we take derivative, half is a constant multiple, it stays the same. Take derivative for ln, we get 1 over the inside function, then times the derivative of an inside function. That's 2x plus 2. For the second function here, take 1 over the inside function, s cubed minus x, then times the derivative of the inside function. That's 3x squared minus 1. And then for the final answer, we bring 2x plus 2 to the numerator and bring 3x squared minus 1 to the numerator. We get 2x plus 2 over s squared plus 2x minus 3x squared minus 1 over s cubed minus x. Taking derivative this way is much easier than taking derivative directly. Next example, f of x equal to ln of e raised to 3x times x to the power 4 plus x over square root of s cubed minus 2x. In order to make the problem a little easier, let me use law of logarithm to simplify this function first and then take derivative. So first of all, we have division here. By the second law of logarithm, we can convert division to subtraction. So function f can be rewritten as ln of e raised to 3x times s to the power 4 plus x minus ln of square root of s cubed minus 2x. Next, I can convert multiplication to addition by the first law of logarithm. I can convert multiplication to addition. So I get ln of e raised to 3x plus ln of x to the power 4 plus x minus ln of square root can be written as the power of a half. So it can be written as ln of s cubed minus 2x raised to half. Next, by the third law of logarithm, we can bring exponent to the front. If I bring 3x to the front, I get ln of e. And for the second term, leave it the way it is. We get s4, s to the power 4 plus x. For the third term, I can bring half to the front. I get half of ln of s cubed minus 2x. And here we know that ln of e is 1. ln of e is 1. So f of x can be written as 3x plus ln of s to the power 4 plus x minus half of ln of x to the power 3 minus 2x. then take derivative. Simplify completely, then take derivative. Derivative of 3x is 3. For ln of x to the power 4 plus x, use chain rule. Take 1 over the inside function times the derivative of the inside function. That's 4x cubed plus 1. For the third function, half is a constant multiple, it stays the same. And then for ln function, use chain rule. Take 1 over the inside function times the derivative of the inside function, which is 3x squared minus 2. Then simplify. Leave number 3 the way it is. Bring 4x cubed plus 1 to the numerator. We get 4x cubed plus 1 over x to the power 4 plus x minus half times bring 3x squared minus 2 to the numerator. So half times 3x squared minus 2 over x cubed minus 2x. That's the derivative of this function. Next example, f of x equal to x to the power of square root of x. How can we take derivative for this function? When we have x on the base and exponent at the same time, we can find this derivative directly. What we can do is, we can apply ln on both sides first. Apply ln on both sides. We get ln of f of x equal to ln of x to the power of square root of x. Apply function ln on both sides of the equation first. Then simplify the right side using the rule of logarithms. The law of logarithms, the third law of logarithm says if there's exponent, we can bring exponent to the front. So ln of f of x equal to square root of x times ln of x. If I bring the exponent to the front, I get square root of x times ln of x. Next, we take implicit differentiation. That means take derivative on both sides, then solve an equation for f prime of x. Take derivative on both sides, then solve an equation for f prime of x. If we take derivative on both sides, on the left side here, we get 1 over f of x times f prime of x. Let's chain rule. 1 over the inside function times the derivative of the inside function. On the right side, use product rule. On the right side, use product rule. So derivative of the first times the second plus the first times derivative of the second. And then simplify. We get 1 over f of x times f prime of x. Here, half times x raised to a half. That's 1 over 2 square root of half times ln of x plus square root of x times 1 over x. Then I can multiply both sides by f of x. I can multiply both sides by f of x. So f prime of x equal to f of x times this function. This function can be rewritten as ln of x over 2 square root of x plus square root of x over x. I bring ln of x to the numerator, and I bring square root of x to the numerator. Then for the final step, replace f of x with x square root of x. For the final step, replace f of x with x square root of x. That's the derivative of this function. Next example, f of x equal to cosine of x to the power of x. When we see x on the base and exponent at the same time, we can find the derivative directly. So I need to apply ln on both sides first. Apply ln on both sides first. We get ln of f of x equal ln of cosine of x to the power of x. Then simplify the right side. For the right side, I can bring exponent to the front. I get ln of f of x equal to x times ln of cosine x. Then, next, take implicit differentiation. For implicit differentiation, we take derivative on both sides. Then, solve the equation for f prime of x. Here on the left side, if I take derivative, I get 1 over the inside function times the derivative of the inside function, which is f prime of x. That's the left side. For the right side, use product rule. Derivative of the first times the second plus the first times the derivative of the second. For ln of cosine x, if I take derivative, I get 1 over cosine x times the derivative of cosine x. Derivative of cosine x is negative sine x. Then simplify. 1 over f of x times f prime of x equal to ln of cosine x plus times positive negative together is negative. So we get minus sine x over cosine x. Then next, I can multiply both sides by f of x. If I multiply both sides by f of x, I get f prime of x by itself. So I have f of x times ln of cosine x minus sine x over cosine x is tangent x. Then for the final step, replace f of x with cosine x to the power of x. The bracket stays the same. ln of cosine x minus tangent x. That's the derivative of this function. Next, let's look at a special one. Let f of x equal to ln of absolute value of x. How can we find its derivative? Let f of x equal to ln of absolute value of x. How can we find its derivative? So, for absolute value, we need to consider two cases. If s is greater than or equal to 0, then absolute value of x equal to x. If x is less than 0, then absolute value of x equal to negative x. So for absolute value, keep this idea in mind. If what's inside is greater than 0, then absolute value of x is the same as x. If what's inside is less than 0, then absolute value of x is negative x. So here also need to consider two cases. If the inside is positive or negative. For ln function, we cannot plug in 0. So only consider x is greater than 0 or x is less than 0. So case 1. If x is greater than 0, then f of x equal to ln of x. If I take derivative, f prime of x is 1 over x. That's case 1. In case 2, if s is less than 0, then f of x is ln of negative x. If x is less than 0, absolute of x is negative x. Then if we take derivative, here you use chain rule. F prime of x is 1 over the inside times the derivative of the inside, which is negative 1. If we simplify, double negative become positive, we get 1 over x. So in both cases, we get exactly the same answer. That means f of x, f prime of x equal to 1 over x if s is not 0. If s is 0, this function is undefined, therefore it's not differentiable. But if s is not 0, f prime of x is 1 over x, which means since the derivative of f of x is 1 over x, which means the entire derivative of 1 over x go back to f of x. So note, since the derivative of ln of x equal to 1 over x for x not equal to 0, then the entire derivative of 1 over x dx it go back to ln of x plus c for x not equal to 0. So for the entire derivative about natural logarithmic function, keep this formula in mind. Integral of 1 over x dx equal to ln of absolute value of x plus c for x not equal to 0. Keep this formula in mind. Next, let's look at some examples. Evaluate each of the following integrals. First integral, integral of s cubed plus 2s squared plus 3x over 4s squared dx. How can we take integral for this function? Let's simplify the function first. First of all, it can be written as s cubed over 4s squared plus 2s squared over 4s squared plus 3x over 4s squared dx. Then, if we keep simplifying, s cubed over s squared, I can subtract the exponent. 3 minus 2 is 1. So we get x over 4. For the second term, s squared can cancel. 2 over 4 is a half. For the third term, we have 3x over x squared. We can cancel 1x from top and bottom. So we get 3 over 4x dx. Next, the first term, s over 4, can be written as 1 over 4x. Half stays the same. And for the third term, 3 over 4x can be written as 3 over 4 times 1 over x dx. Next, take derivative for each term individually. For the first term, we get 1 over 4 s squared over 2. For the second term, half is a constant, so we get half times x. For the third term, 3 over 4 is a constant multiple, stays the same. For 1 over x, its entire derivative is ln of absolute value of x. For 1 over x, its entire derivative is ln of absolute value of x plus c. Then if we simplify, 4 times 2 is a. We get s squared over a plus s over 2 plus 3 over 4 ln of absolute value of x plus c. That's the integral of this function. Next example, integral of s cubed, s squared over s cubed plus 1. Integral of s squared over s cubed plus 1. For this function, we can use u substitution. If I let u be the denominator, what's my du? Here my du will be 3x squared times dx. In the function we have s squared. We are missing a 3. We have s squared. We are missing a 3. 3 is a constant. That's not a big problem. I can divide both sides by 3. If I divide both sides by 3, I get 1/3 of du equal to s squared dx. So this function can be rewritten as 1 over x cubed plus 1 times s squared dx. I put s squared and dx together. Then substitute. S cubed plus 1 is u. S squared dx is 1/3 of the u. Then 1/3 is a constant, I can put it outside. I get 1/3 of integral of 1 over u du. Next, take antiderivative for 1 over u. That's ln of absolute value of u. Antiderivative of 1 over x is ln of absolute value of x. So same thing for 1 over u. The antiderivative should be ln of absolute value of u. So antiderivative of 1 over u is ln of absolute value of u plus c. And then for the final answer, replace u with s cubed plus 1. So the final answer is 1/3 ln of absolute value of s cubed plus 1 plus c. That's the antiderivative of this function. Next example, integral of ln of x over x dx. Integral of ln of x over x dx. How can we take antiderivative for this function? Since we can't find antiderivative directly, think of u substitution. If I let u be ln of x, my du is 1 over x dx. We have x on the denominator. This function can be rewritten as ln of x times 1 over x dx. So here we can see that ln of x is u. 1 over x dx is du. So you get u times du. Next, take antiderivative. We get u squared over 2 plus c. For the final answer, replace u with ln of x. We get ln of x squared over 2 plus c. That's the antiderivative of this function. Next example, integral of secant squared x over 1 plus tangent x dx. How can we take antiderivative for this function? Since we can't find antiderivative directly, so think of u substitution. For u substitution, if I let u be the denominator, 1 plus tangent x, then du is secant squared x dx. Derivative of tangent x is secant squared x. Then we have secant squared x here. So this function can be rewritten as 1 over 1 plus tangent x times secant squared x dx. Then we can substitute. 1 plus tangent x is u. Secant squared x dx is du. If we take antiderivative, 1 over u, for 1 over u, its antiderivative is ln of absolute value of u plus c. And then for the final answer, replace u with 1 plus tangent x. We get ln of 1 plus tangent x. Plus c. Next example, how can we take antiderivative for tangent x? How can we take antiderivative for tangent x? For tangent x, we can try to rewrite tangent x as sine x over cosine x first. Next, let's apply u substitution. If I let u be the denominator, if I let u be cosine x, then my du is negative sine x dx. We have sine x, we have dx. What's missing is negative sine. That's a constant. Consider this is negative 1 here. So I can divide both sides by negative 1. I get negative du equal to sine x dx. This function can be rewritten as 1 over cosine x times sine x dx. Then substitute. We know that cosine x is u. Sin x dx is negative du. Then negative 1 is a constant, I can put it outside. Negative 1 is a constant, I can put it outside. I get negative 1 over u du. Then take antiderivative for 1 over u. Antiderivative of 1 over u is ln of absolute value of u plus c. And then for the final answer, replace u with cosine x. I get negative ln of cosine x plus c. If we keep simplifying, we can consider this is negative 1 in the front. When there's a coefficient in front of ln, I can bring it back as exponent. That's the third law of exponent. That's the third law of logarithm. When there's a coefficient in the front, I can bring it back as exponent. That's the third law of logarithm. I can write it as ln of absolute value of cosine x raised to negative 1 plus c. This can be rewritten as ln of 1 over absolute value of cosine x. And we know that 1 over cosine is secant. 1 over cosine is secant. So this function can be written as ln of secant x. Since 1 is always positive, I can bring the inside absolute value. And 1 over cosine is secant. So antiderivative of tangent x is ln of absolute value of secant x plus c. So keep this formula in mind. Integral of tangent x is always ln of secant x plus c. Keep this formula in mind. So this is the antiderivative of tangent x. Next example. How can we find antiderivative for secant x dx? So the way to find antiderivative for secant x is very, very tricky. The way to find antiderivative for secant x is very, very tricky. For secant x, I first of all rewrite secant x as secant x over 1. Next, for secant x over 1, I multiply the top and the bottom by secant x plus tangent x. Multiply both the top and the bottom by secant x plus tangent x. Multiply both the top and the bottom by secant x plus tangent x. The way to find antiderivative for secant x is very, very tricky. Here I multiply top and the bottom by secant x plus tangent x. On the top, if I distribute secant, I get secant square x plus secant x tangent x. If I distribute secant, I get secant square x plus secant x tangent x. On the bottom, 1 times secant x plus tangent x is secant x plus tangent x dx. Next, we make u substitution. Let u be the denominator. Let u be secant x plus tangent x. If I take du, what do we get? Derivative of secant x is secant x times tangent x. Derivative of tangent x is secant square x dx. That's exactly the same as our numerator here. This is exactly the same as a numerator. So this function can be written as 1 over secant x plus tangent x times secant square x plus secant x tangent x dx. If we substitute, we can see that secant x plus tangent x is u. Secant square x plus secant x tangent x dx That's exactly the same as du. Then take antiderivative. We get ln of absolute value of u plus c. For the final answer, replace u with secant x plus tangent x. So that's the antiderivative of secant x. This is an antiderivative of secant x. So memorize this formula. Integral of secant x dx equal to ln of secant x plus tangent x plus c. Memorize these two formulas.